Okay, let's turn next to the Poisson distribution. And the Poisson distribution is used for questions like what's the probability of observing X events per a certain time or space interval when the average number of events is lambda. Okay, so the Poisson distribution was developed or identified by Simeon Denis Poisson, who lived from 1781 to 1840, and the formula only takes two parameters, which is X, the number of successes, and lambda, the average number of successes per time. And then the formula is lambda raised to the number of successes times E raised to the negative lambda over X factorial. And you see, this is already a formula which is a little bit more puzzling, or not as intuitive as maybe the binomial distribution, but what we will do is we will just work with it. And E is the 2.718, and that is what you get from infinite compounding. So let's say, if you get 100% interest rate and you get it at the end of the year, then $1 will grow into $2. But if the interest rate, if you get twice the interest rate, so you get 50% after 6 months, then after 6 months you go from $1 to $1.50, and then at the end of the year you get again 50%, but then you get the 50% on the $1.50, you end up with $2.25. And as n goes towards infinity, we approach the number E. And let me just illustrate it maybe in Excel. So we have here n, which is the number of, I call it interest payments, right? So, and initially, okay, we are in period 0, and your end of year value is, okay, let's say 1. Okay, so now if you get 100% interest rate in 1 year, then what happens is that your previous value is multiplied times 1 plus the 100% interest rate. So 100% is 1, and this is raised to 1. And then at the end of year 1 you would get 2. But if your number of interest rates are paid twice, so you get 50% after 6 months, then we would say, well, this is equal to the initial value of 1, and then you get 50%, which is plus 1 over n, and you get that n times. So raised to the n, at 2.25. Okay, and we get 3. So that means after 4 months you get 33%, and then after another 4 months you get another 3%, 33%, and so on. So in this case, you would get 1 plus 1 over 3, so that's 0.33, and that's 3 times, so raised to the 3. Okay. Well, and now let's just assume that you do that, I don't know, 1,000 times, so, or 100 times, so I continue that series at 3, and I extend it to home, edit, fill, series with a step value of 1, and I want to stop at 100. And now I just can copy down that formula, and then we can see that there's something wrong here. So we were here at 3. You see, I hard-coded here the 3 instead of picking it up from here. That means here's still a 3, not a 4. So I need to copy down from here. And then you see we approached at 2.7, which is the number E. Well, and if we just draw it, we can see what that looks like. So you see that the more often you compound and you basically eventually get to continuous compounding, you approach the value of 2.7, which is that number E, 2.718. And actually in Excel language, the number E can be called upon with EXP1, and that is the number E, 2.71828. Okay, so in Excel, E would be and that's the 2.718. Okay, so that's an interesting formula. And so the mean, the number of occurrences, is known. So lambda is the mean. But what makes this formula interesting is it's also equal to the variance. So that means that the standard deviation is the square root of lambda. Okay, but let's just apply the formula and then also show how that works in Excel. Okay, so in a light chain, there is an average of 2 malfunctioning lights per foot, which has 30 LED lights per foot. Okay, so this would be an example for a certain average per space. So in this case, we would say our lambda is 2. And now we want to know, determine the probability that exactly 4 lights are malfunctioning. So that is x equals 4. And that's it. So now we just need our formula. So we would write what's the probability of getting x equals 2 successes. So the defect light bulb is considered a statistical success. When it's actually 4, x equals 4 when the average is 2. given that lambda, on average we have 4 defect. Okay, so now this probability would be written as 2 raised to the 4 times, in Excel we would write exponential 1 raised to the negative lambda, negative 2, divided by x factorial, which is 4 factorial. Well, because of the presence of the e, it cannot be easily calculated by hand. You can also look up tables, but they don't become super convenient now. So let's just focus on Excel applications for now, and let's see how we solve that in Excel. Okay, so if we have here our formula, well, what we could do is we could write that the probability is, now just maybe start a new sheet. So maybe here we would say, okay, the probability, so I want to enter that formula now into Excel. So we would say this is equal to 2 raised to the 4 times exp1 raised to the negative lambda 2, okay, divided by factorial of 4. We get 0.09, so roughly 9%. Of course, in practice, you wouldn't do it that way because, as you probably can guess, there is a distribution for it. And you just, whenever you search something in Excel, like Poisson, you start with Poisson and then you already have it. You see Poisson dist returns the Poisson distribution, and now x, what's the number of successes? Set 4, and then what's the mean? 2. Do you want it cumulatively, yes or no? Well, we don't want it cumulatively, we want to know that we get exactly 4 and not 0 or 1 or 2 or 3 or 4, so we put in a 0. And then we get the same 9%. Okay, so we could also look again at the distribution. So maybe I'll start with x. Maybe I'll do it from 0 to 10 or 15. So home, editing, fill, series, stop at 15. So by 15, actually 14, 15. By 15 the probability should be so small that the probability distribution levels out. Okay, so let's take a look at what it looks like. So the probability is probability equals Poisson dist. Okay, I want to know 0 successes if the mean is 2, and I don't want it cumulatively, so 13%. And now let's copy this down. And you see that after the 10th observation we have so many zeros that there is really no need. Even 15 seems to be too long. But we can also look at the cumulative probability. and then we would say Poisson dist. I want to know 0, mean is 2, and now I want it cumulatively. Okay, so for 0 it's still the same, because cumulatively 0 successes is the same as 0 successes. But now that should approach 1 if I copy it down. And that's what it does. If we draw it, or if we want to look at the distribution, insert recommended chart. Okay, so it looks something like this. Well, it looks a little bit weird. So whenever you have something like this and you suspect that this is actually more smooth, you can always choose the option under that formatting bucket and smooth the line, and that's probably more accurate. Then we can also look at the cumulative probability. Okay, let's put that. So we highlight the first row that goes on the x-axis, then cumulative probability that will go on the y-axis, insert recommended chart, and you see that it approaches very quickly the 1. So those would be the two formulas and how we can illustrate that. So, okay, to draw in Excel the probability distribution for 0 to 30 defect, and we did it for 15. Let's change it to 15. Okay, so that is how we can use the Poisson distribution. And again, this is just another discrete probability distribution where we essentially count certain events. But it is different from the binomial distribution in the sense that we know an average frequency, and then we want to know what's the probability that we have a certain number of occurrences given a certain average number of occurrences. Okay, let's just stop here, and then let's continue in the next one with the hypergeometric distribution.